Okay, well, welcome back, everyone. So in this video, it's following up on the prior video where we're talking about the IEEE 754 floating point standard, and in this case, we're going to do something, we're going to go a different direction, okay? What we're going to do in this case, unlike the prior video, is we're going to start with a base 10 number, okay, base 10 number, and we are going to convert it into a binary IEEE 754 floating point standard, okay? And to do this, we're going to do this following this 7-step process, okay? 7 steps involved, so it's a little bit more complicated than going the other direction, okay? But you get used to it, you do a few examples, and it's not so bad, okay? So what I want to do is I want to basically walk you through these 7 steps and kind of explain what we're doing. And we're going to do this as a single precision floating point, which means we're gonna do this where it's a 32-bit number, but the process is nearly identical if we're doing double precision. Okay, so the first step is we want to take this base 10 number, okay, this 5 1/4, okay, and we're gonna express it as a fraction. All right, and our goal is to have it and so that we've got integers, okay, in the numerator and denominator, okay. And we're going to do it in such a way in which we're going to be dealing with powers of 2, right? So that we're going to continue to double the size of the denominator until we no longer have a fraction in the numerator, right? So as we go through this and we say, okay, let's say we've got 10.5, right, over 2. Well, we've still got this fraction, so we're going to go forward further, right? We're going to double the denominator again, right? And we're going to get this to be our 21, okay? Our 21. All right, so we've written it as a fraction, okay? Now what we want to do is instead of having these numbers here represented in terms of base 10, right? In terms of base 10, we're going to represent them as in binary. Okay, so effectively we're going to have our 21, right? That being 10101 is 21 in binary, and then we've got, of course, 4 in binary represented as 100. Okay, and this is all represented in this case in binary or base 2. All right, so we've taken that fraction above and we've just converted it into representing it in binary, okay? And the next thing we're going to do is we're going to represent that same number, but we're going to do it in scientific notation. All right, scientific notation where we're always going to be dealing with powers of 2, because now we're in the binary universe. We're going to do this in terms of powers of 2. All right, so we're going to take this number, right, and we're going to express it as, we're going to put it, since it's in scientific notation, we're going to have 1 point, right, 1 in the decimal point, and then the rest of the number, okay, we're taking that 21 that was above, right? We're taking the same number that was here, right? And we're representing it in scientific notation. So since we had to move the decimal point then over by 4, right? Or in the case we're dividing by 4, right? We're going to express that in scientific notation as multiplying by 4 or 2 squared, right? Okay. All right, so we've got, remember, we're dealing with equals here the whole way down each one of these steps. We're really taking the same number and we're just representing it in different ways, okay? So we're taking the 5 1/4, right? We're expressing it in a fraction where the denominator is a power of 2, right? We're then expressing that in binary and then taking that number and expressing it in this scientific notation where we're dealing with powers of 2, not powers of 10, okay? All right. Now we start to be able to kind of pull this apart in terms of these different components of our IEEE 754 floating point standard. Okay, so if you remember from the prior video, we've got 3 different parts of that, of how to represent it. And we can always look at the documentation to assist us, right? We've got the sign bit, we have an exponent, right? Single precision's 8 bits for the exponent, right? And then the rest of the bits are the fraction. All right, so let's look at each one of those components. Sign bit's easy, right? Sign bit's easy. Well, 5 1/4 is positive, right? Sign bit 0. 0 for positive, 1 would be for negative, a negative number, right? That one we could know right off the bat. It's a very, very simple, very simple calculation, okay? The exponent, all right, we're going to get the exponent by looking at this number here, okay? To get it in a scientific notation, we were raising 2 to the power of 2, okay? So we want to figure out the exponent, right? We're trying to figure out the exponent. We look here at the equation, and we can recall that the exponent is, we're going to take the exponent, we're going to minus the bias, all right? And we know that this is going to be equal to 2. So let's take this expression here, right? And what do we know, right? We're trying to find the exponent, right? We're trying to find the proper exponent. Okay, we know the bias is going to be 127, right? We know that because that's just a definition here of the single precision bias, okay? And we also know that the result of that is going to be 2, right? How do we know that the result of that needs to be 2? Well, we figured that out over here, right? When we wrote it into this normalized scientific notation, we were raising it by a power of 2 to do that, okay? That's how we determine that this must equal 2, right? So then we obviously know that the exponent has got to be 129, okay? All right, so we've solved for that. The exponent is 129 in base 10, okay? And if we were going to write that in binary, that's going to be the following. In binary. Okay. All right. So we've got 2 key pieces of our representation here. For the 754 standard, we now have the sign bit and we have the exponent. The rest is the fraction, right? The last part is the fraction. So how do we get the fraction? That's actually quite simple, right? We've really already found the fraction. We've got this number here. Everything to the right of the decimal point is going to be the fraction. Okay, so the fraction is 0, 1, 0, 1, and then the rest is going to be all zeros for whatever number of bits that we have. Okay. Once we have that, right, step 7 is basically just writing them all together. Okay, it's writing everything together. So it's like just taking those steps 4, 5, and 6 and just putting them together to get the definition, to get the final result. Okay, so it's not even much of a step. It's just kind of gluing the different pieces together, right? We look at that and we know, right, just to kind of recap here, we have this documentation. We know we have 1 bit for the sign bit, then we have 1 byte or 8 bits for the exponent, and then everything else is the fraction, right? So we're going to just go ahead and write that. We've got our sign bit. Okay, then we have our exponent. Let's make sure I don't mess up any of the zeros here. I'm going to try to write it with 4 bits and then a space. Okay. Okay, that's our exponent, right? And then we can even draw where the different pieces are. Okay, and then we have our fraction. Okay, and the fraction is our 0, 1, 0, 1, and then the rest, oops, let's get the colors right. And the rest is going to be all zeros. Okay, so 1, 2, 3, 4. To be precise, since it's 32 bits, it's going to be that. Okay. That's our result. Okay, as a single precision floating point number. Now, what we really should do, though, is do a little bit of a sanity check, right? We should do a sanity check and just confirm that this actually is correct. So why don't we take this number, this binary number, and let's do what we did in the prior video, and let's go and convert this back, right, into a base 10 representation. And let's make sure that we know that if we did it correctly, we should be getting 5 1/4. Okay. So let's do that, and then this will just kind of confirm that we didn't make a stupid mistake or mess something up along the process. Okay. So if we do that, right, I'll just give myself some, let's have some more room to work here, right? We know that the sign is 0. We know that the exponent is 129. Okay. And we know the fraction is, and I'm going to keep the fraction in represented in binary here, is 0, 1, 0, 1. Okay. So let's use the formula that we saw previously. Let's go ahead and let's use this formula to confirm that everything is working correctly. All right. So we've got the formula right here, right, where we have our definition is we have -1 times the sign bit. Okay. And then all I'm doing is just following this formula, right? Then we have 1 plus the fraction. Okay, and then the last piece here, again, just going back and looking at this, is times 2 exponent minus the bias. Okay. Okay, so let's start filling in what this means, right? We know that this term, again, just like the prior video, since we're raising to the power of 0, that's just going to drop out. Okay, so let's say, well, what is our fraction? Okay, our fraction here, let's remember that the fraction, this bit would represent 1/2, this one's 1/4, right? This one is 1/8, and then we have 1/16. Okay, so if we do that, right, we're going to get, we can represent this in terms of 16ths, right? We're going to have our 1 plus 5/16. Okay. And then we've got our times 2 raised to the exponent. We know our exponent is 129 minus the bias. So it's going to be, the bias we know is 127. So we're going to have times 4, right? 2 squared. All right. And if we do all of this, let's just plug this into a calculator real quick. And we should get a result in which this is 5 1/4. Okay, and we're going to times that by 4, and we get 5 1/4. Okay, so everything checked out correct. So we know, right, we just did a check to make sure we didn't make a mistake along the way. We confirm that, yep, this is correct. We did convert that prior, in the prior example here, that we did convert that into a IEEE 754 floating point number successfully. Okay, so we'll stop there, right? There's a bunch, there's a number of steps here. It's good to practice them a number of times, some different examples to make sure that you let it really sink in and get used to it, right? We will follow up at a later point where we'll look at how this kind of connects to hardware, right? And how there's different hardware resources that are needed for the computation and processing floating point numbers. And that does kind of connect to how the information is stored and represented, is designed in a certain ways to aid and assist the processing and to make it scale. But that is for a different time. All right. Thanks for watching, and talk to you soon.